So let's look at monochromatic light. So monochromatic diffraction. And again, just in case, just for clarity, monochromatic just means one wavelength. So what we need to be able to say is how the slit width and the so how the slit width, remember that was B, and wavelength lambda affect the diffraction. Diffraction pattern width is normally what we're asked about. So all we can do is go straight to our formula, which says that theta is equal to lambda over B. Well, theta is the angle when we get our first minimum. So if I have small theta, then that means that the minimum is really close to the center of the screen. So small theta means small width. Okay. Like what we can also do is if I know this is my slit, say here, and I know that my first angle theta is, say, this angle, well, I can then look at using trigonometry. So if I know this distance d and I want to find this height up the screen x, well, I've got the opposite on the adjacent side. So tan theta is equal to x over d. So x equals d tan theta. And basically, this shows that whatever theta is, if it's small, then tan theta is small, so x is small as well. So that just sort of backs up what we saw here. And to get small theta, that means I either need small wavelengths, which means high frequency. So that's going to mean something like blue is going to be smaller than red. Come on, don't give up now, pen. And I want a big B, which means a large slit, which kind of makes sense. If I've got a really tiny slit, then it's going to diffract loads because the slit width gets closer and closer to the wavelength. And we know that we get the most diffraction when the wavelength and the slit width are similar. So we want a large slit is better. A large slit gives smaller pattern. I'll just make a note of what I said. Remember, if B is roughly equal to lambda, then we get lots of diffraction. And that's horrible. I mean, in terms of the blue comment, think about what's happened with DVDs. I mean, I don't know if you remember back in the day when DVDs first came out, but they always had a red light on them. But now we have Blu-ray players, which use blue light because we get better diffraction, and diffraction is really useful in reading media. Now, we also need to be able to comment similarly on if I've got white light. And really, it's the same idea. So everything we said before is perfectly fine. The longer wavelengths have their first minimum wider. But remember, whenever you ask about white light, always start by saying that this has all wavelengths of the visible spectrum. And what's going to happen is at each value of theta, a wavelength will be absorbed. Or a wavelength is absorbed. Starting with shorter, or with the shortest wavelengths. So that's going to be, say, purple light. With purple lights absorbed, then we're going to see all the light that isn't purple. So from that, the complementary color is shown. At each lambda, sorry, at each theta. And then finally, so that would be 2 marks. And then the third mark, which almost everyone misses because they're thinking so much about this sort of destructive interference, for any diffraction pattern, the pattern gets dimmer as theta gets larger. You remember right at the start, the thing we drew, the intensity pattern was much lower down and had much lower intensity as soon as we got away from our central maximum. Okay. But we never see white light. We essentially get, let's go back to blue to sort of bounce off that point, sort of rainbow spectrum, which sometimes gets mentioned in the mark scheme for deserving credit. So it may be worth saying that's all. Okay. Last slide of information. And we're just going to go through calculation methods. So, I mean, this is what we do at the end of every topic, because the explanations and the definitions you just need to learn. These methods are worth learning if you know there's a certain type of question that always gets you stuck. Now, they can really only ask you for one thing. So they can only really start with theta equals lambda over b. Okay, now things to be careful of, let's star them. Lambda will often be in nanometers. B will often be in millimeters. And as always, we want both of these to be converted to meters. Okay. Once we know our theta, what I'm going to do is I'm just going to redraw the diagram that I had 2 slides ago. So if I know theta, and we had it in the first right angle triangle we drew, but then also from our slit to our screen. So that's theta. This is the height to the first minimum. And this is going to be, well, this is 0, and we're going to call this d. And remember we said that the height is equal to d tan theta. And something else that's worth learning is that for very small theta, tan theta is roughly equal to theta. I mean, if you, again, depending how much maths you want to be able to think about, tan theta is roughly equal to sine theta, well, no, it's always equal to sine theta over cos theta. Now for theta roughly equal to 0, sine theta, we said already goes to theta, and cos theta will roughly go to 1. So we end up with tan theta is roughly equal to theta over 1, or theta. So we get that the height up the screen of the first minimum is d theta, or d lambda over b. So those are the 2 things they can ask you to do. 1, find the angle of the first minimum. Remember, once we know that one, we can find all other minima just by multiplying it by 2, 3, 4, or whatever. And then we may have to find the height up here to get our next 2 marks, say. Okay, we don't have very long left, so I'm going to go straight onto the questions before seeing if you have anything you want to ask. So, highlighter out. So, single slit, which means we know it's relevant, and we've used light of different colors. The width of the central peak is measured, so we're looking at the width. What is the order of the colors that corresponds to increasing widths? So that means I want, as I go across, I want theta to be increasing left to right. And because I've got different values of wavelengths, or different colors, which corresponds to different wavelengths, I need lambda over b to be increasing, which means I need the wavelength to be increasing. So remembering that red is the longest and blue is the shortest, straight away that's just going to be C. Okay? It's really good knowing your visible spectrum really well. Just be careful, like so many people would have put red, green, blue because they are rushing it. So always just make sure you put it in the correct order. Now we've got a parallel beam of coherent light of wavelength lambda, incident on a rectangular slit of width d, and then the screen that it's shone on is a distance d, where d is much greater than d. Sorry, big D is much greater than little d. What's the width of the central maximum? Okay, so let's draw a diagram again. So this is why I gave you the other diagram at the end. So if this is my slit, so let's draw across from the middle, and that's going to be our x equals 0. And we have our first minimum, remember we said is theta equals lambda over b. Okay. Now the central width, well, let's find the width of this, so from 0 to here. If this is d, remember we said that x was equal to d times theta, which is equal to d times lambda over b. Not b, d. Ugh. But I wanted the central width, so it's not just this, it's also going to be this bit. So that's also going to be x equals d lambda over little d. So the overall width is equal to 2d lambda over little d. So A. Okay. Always be careful with what they've asked. They could have said the height of the first minimum above the central position, which would have been C. Okay. This 2 is because we wanted the whole width. Electromagnetic waves pass through a slit in a metal plate with minimal diffraction. So there's our keywords. We're not getting much diffraction. The slit has a width of 0.25 meters. What is the wavelength of the waves? Now in topic 4, we did diffraction just descriptively. So we could have used our knowledge here, but I'm going to answer this question using the equation we have. Well, theta equals lambda over b. And if I've got minimal diffraction, then that means that theta is very small, like very, very small, which means that either lambda is very big, not very big, very small, or it means that b is very big. Well, because I've been asked about, I've been given the slit width, what is the wavelength of the waves? Well, for this to be very small, I need lambda much less than b, so it's going to be A. I think every answer so far has been A. Oh no, almost every answer has been A. Okay. Now, final question, and then I'll see if you have anything you want to ask. We're given light with a wavelength of 620 nanometers, and we've got a slit of width 0.45 millimeters. See what I said? I called it. After passing through the slit, the light is incident on a screen that is 3.4 meters from the slit. Calculate the distance between the center and the first minimum of the diffraction pattern. Well, we've been asked for the first minimum, so we know that we're going to be using theta equals lambda over b. So it's going to be 620 times 10 to the minus 9 over 0.45 times 10 to the minus 3. And that's going to equal 1.38 times 10 to the minus 3. It's nice and it's really, really tiny. So, I mean, I'm just going to do sine of it because I can. And I get the exact same answer, pretty much, to 6 decimal places. Now, we said that the height up along the screen is equal to the angle times the distance. So it's going to be 1.38 times 10 to the minus 3 times by the 3.4 meters. We ignore this for now because diffraction only happens along this width. So our final answer here, goes with a deep breath, is 0.0468 meters, or let's check our significant figures, 222 4.7 centimeters.